Welcome back. Now, our goal here is to swing a sword at an enemy, and that sword is going to hit the enemy from a particular direction. And we have 4 different hit react animations that cause the enemy to stumble in a specific direction. Now, we want to be able to swing the sword and hit the enemy from one side and make the enemy stumble to the other side. So if we're swinging our sword from the right side here, the enemy should go to the left. But if we swing the sword from the other side, the enemy should stumble the other way, to the right. So how exactly do we figure out which direction the enemy should stumble in? Well, let's think about this from the point of view looking down at the enemy from above. So here's the enemy. This yellow circle is the enemy's head, and here's the enemy's forward vector. So the vector pointing straight out in the enemy's own forward direction. And we could be swinging the sword from anywhere. And as soon as our sword's collision box overlaps with the enemy, we perform the box trace down the blade of the sword and get a hit location, an impact point. We can use this information to figure out which direction the enemy should go when it plays its hit react animation. So what we can do is we can make a vector pointing to that hit location. This allows us to know which direction that hit location is from the center of the enemy. So we can call this vector toHit because it's from the enemy's location, or the center of the enemy, to the hit location that we got from our box hit. Now, you should know how to calculate this vector. It's the impact point minus the actor's location itself. Here are the 2 points in question. This is the impact point generated from our box trace, and this is the actor location of our enemy that we can get using getActorLocation. So subtracting the tip location from the tail location gives us this vector. So now that we have this vector toHit, and we have the enemy's forward vector, we want to know what the angle is between these two. That's going to give us the information that we need to figure out which hit reaction to play. Let me explain this a little bit. Let's consider that if the enemy gets hit from the front, it should stumble backward. In other words, that angle between forward and toHit should be small, less than 45 degrees and greater than -45. But in this picture, it's not in that quadrant. It's actually less than -45 and greater than -135. That means the character should stumble the other way. So this angle here between these two vectors is really what we need to know. And once we have it, then we can figure out which direction to stumble. Let's consider that these are the 4 directions, at least from the enemy's point of view. And if this angle between forward and toHit is in between -45 and +45, we should play the montage section from front because we're getting hit from the front and we'll stumble backward. However, if this angle is less than -45 but greater than -135, we should play from left because we're getting hit from the left. That's what the green arrow depicts in our diagram here. Now, if the angle is greater than 135 and also less than -135, we should play from back as the character's getting hit from behind and needs to stumble forward. And finally, if the angle is greater than 45 degrees but less than 135, we should play from right as the character's getting hit from its right side. So we know the values that we should check with this angle, and we can use that to play the correct animation. The question is, how do we actually calculate the angle between two vectors? And that is where the dot product comes in. If we have 2 vectors, call them A and B, then if we place these vectors so that their tails are touching, there is some vector in between them. I'm using the Greek symbol theta here to represent that angle. The mathematical definition of a dot product is defined as follows. We say that A dot B, or the dot product of A and B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. In short, we could say A dot B equals AB cosine theta. Now, if we try to solve this equation for theta, we can divide both sides by the magnitudes of a and b to isolate cosine of theta on the right side. Now, this is one of those situations where it's really handy if a and b are normalized. That would mean their magnitudes are both 1. So this equation would simplify to a dot b equals cosine theta. So in general, in games, if we're taking a dot product, we typically normalize a and b so their magnitudes are 1 just to simplify this equation. Now, the equation looks a great deal simpler. We just have cosine of theta on the right side, but we want theta, not the cosine of theta. So how do we solve this? Well, in addition to the trig functions like sine and cosine, there exist the inverse trig functions. One of these is the inverse cosine, also known as the arc cosine. Whenever you see ACOS or arc cosine, that's the inverse cosine. And if you take the inverse cosine of the cosine of theta, then you get theta. So the inverse cosine cancels out the cosine. That's how we can isolate theta. And if we take the arc cosine of the right side of the equation, we have to take the arc cosine of the left side of the equation. So now if we take the arc cosine of a dot b, that gives us the arc cosine of cosine theta, which equals theta. So we've solved for the angle. Now, this all may sound very complicated, and at this point, I don't want you to get discouraged. This is all happening behind the scenes for us when we're game programming, but it's important that you understand mathematically what's happening and what the dot product actually is. This is the mathematical definition of the dot product, and this is how it's implemented in the math libraries in Unreal Engine. So it helps to understand what you're doing when you take a dot product. So now that we understand how we can figure out the angle between two vectors using the dot product and the inverse cosine, also known as arc cosine, let's see how this works in the engine. So I'm back in enemy.cpp here in getHit, and we have the impact point. Now we need a couple of vectors. We need the forward vector, and we need that toHit vector. And we saw how we can calculate those, so let's do it. I'm first going to make a const f vector called forward. And this is easy. It's simply the forward vector of the enemy, which we can get with getActor forward vector. Next, we need toHit. So let's make a const f vector called toHit. And as we discussed in the slide, this is going to be the impact point minus the location of the enemy, which we can get with getActor location. Now, toHit is not a normalized vector, but the forward vector is. getActor forward vector returns a normalized vector, but we calculated toHit from 2 points in space, and those could be any distance away from each other. And we mentioned that when we use dot products, if we're going to be solving for that angle, it's useful for these to both be unit vectors. So we want to normalize this. And what I can do is wrap this expression in parentheses. So impact point minus getActor location, all in parentheses, and then just outside the parentheses, I can use dot and call getSafeNormal. GetSafeNormal is going to take the vector, which is the result of this subtraction, and normalize it, and then return that result, which we're storing in toHit. So now toHit is normalized. Now, getSafeNormal means that it's going to check to make sure that it's safe to normalize the vector. If you recall back when we discussed normalizing vectors, we learned that to normalize a vector, we divide that vector by its own magnitude. And if its magnitude is 0, then we'd be dividing by 0, which is the most cardinal sin in all of mathematics. It's the kind of thing that would unravel the very fabric of the space-time continuum and destroy the entire universe. So we're going to use getSafeNormal, and that way there's no risk of any of that. So since we have forward and toHit, it's time to get the angle between these two. And we do that using the dot product. So the first thing we're going to do is take the dot product of forward and hit. Now, Unreal Engine's dot product function is a static function that belongs to the f-vector class. So we're going to use f-vector dot product. And we see that dot product returns a double and it takes two vectors, both passed in by const reference. So we're going to pass in forward and we're going to pass in to hit. And the result of this is a scalar. Interesting, right? The dot product takes two vectors and returns a scalar. And that scalar is equal to the mathematical definition that we discussed. I'm going to go ahead and remind you in a comment here. I'm going to say forward dot, we'll just use an asterisk, to hit equals the magnitude of forward times the magnitude of to hit times cosine of theta, which is the angle between these two vectors. But forward and to hit are both normalized vectors. So really this is equal to just cosine theta. Let's go ahead and comment this too. We'll say forward equals 1, to hit equals 1. So forward dot to hit equals cosine theta. So that's what we have returned by dot product here. So why don't we just make a const double called cosine theta, or just cos theta for short. So now that we have the cosine, we need to take the arc cosine. And there's a function for that. It exists in fmath. So we're going to take the fmath function library, and the function for the arc cosine is, not surprisingly, a cos. So a cos means arc cosine, and it takes a double called value. We're going to pass in cos theta. So let's go ahead and make a comment here and say, take the inverse cosine, and in parentheses, arc cosine of cos theta to get theta. So that's what we get. Taking the arc cosine of cos theta gives us theta. So we'll make another const double called theta. Oops, and that should be double. And now we have theta, which is the angle between the two. Now, I mentioned to you back in the lecture where we discussed radians and their relationship to degrees that these trigonometric functions typically use radians instead of degrees. And that's what we get from the arc cosine. We get the angle in radians. So we need to convert from radians to degrees. So what I'm going to do is actually remove the const from theta, so it's not const, and I'm going to reassign the value. I'm going to say theta equals, and we'll convert this from radians to degrees. And fmath has a function for that. It's called radians to degrees. How convenient. So we'll pass in theta, and radians to degrees will take theta in radians, convert it to degrees, and return that. So we'll reassign theta with the angle in degrees. So now theta is in degrees. And now that we have this value, well, we can see what it is. So why don't we do that? Let's go ahead and simply add an on-screen debug message. And remember, to do that, we first check if gengine is valid, because gengine has add on-screen debug message. By the way, that's not all that gengine does. It's actually a very high-level class that manages lots of things for the game, but add on-screen debug message is just one of the capabilities of it. So we can add a key. I'm going to use 1 for the key. For time to display, I'll have 5 seconds. For the F color, I'll use green. And then we need a message to display. I'm simply going to use fstring printf. And let's make some room here. And in printf, I'm going to use the text. The text is going to say theta %f. And after the text macro, I can pass theta in. So be very careful with your parentheses here. The text macro is just this quantity here. So 2 parentheses there. Then the printf function is this quantity here. It has text and theta, 2 inputs, and then the comma. So if you're getting compilation errors, check your parentheses, make sure everything is balanced out and perfect. as the compiler is very unforgiving with these sorts of things. So after our message, I can Control-Shift-Space to see what comes next in our on-screen debug message. And from here on out, we see all optional inputs, so I'm going to leave them out. So we're just going to print the value of theta to the screen. And this is in get hit. So whenever the enemy gets hit, we're going to display that value. Now, in order to get some more visual data along with simply printing this angle, I'd like to see these vectors. I'd like to see the forward vector, and I'd like to see to hit. Now, we do have in our debug macros header file a macro for drawing a vector. Just to remind you, back in debug macros, we have this draw vector. We have one for a single frame, and we have one for a duration. And these are great for drawing vectors, but I'm going to show you something new. I'm going to show you how to draw a debug arrow, which is better than just a line and a point. So here's how we do it. Draw debug arrow is a function that exists in another static library. So we're going to have to include it. It's in Kismet, and it's called Kismet System Library. So we'll include Kismet/Kismet System Library.h, and the function is called draw debug arrow. So to draw these debug arrows, we're going to use Kismet System Library, and the function is draw debug arrow. Pretty simple. Now, these are static functions, so they need a reference to the world. In other words, they need a world context object, but we're in the enemy class, so we can pass in this as the enemy is in the world. Now, the first debug arrow I'd like to draw from the enemy itself straight out in its own forward direction. So its start is going to be get actor location, and its end is going to be get actor location plus forward. But forward is normalized. It only has a length of 1, so I'm going to multiply forward by, say, 60. So that's the end location, the enemy's location plus the forward vector multiplied by 60. Now, the next input is the arrow size. That's basically how big the arrow's pointy head is going to be. We're going to use 5.f. Next, we need the color. I'm going to use fcolor red. And for the duration, we'll use 5 seconds. And that final input is called thickness. We don't need to mess with it. So that's going to be the arrow from the enemy's location straight out. Now we need the arrow from the enemy's location to the hit location. So I'd like to see that vector, the vector that we called to hit. So I'm going to use Kismet System Library. Draw debug arrow. For the world context object, I'll use this. For the start, I'll use get actor location. And for the end, I'm going to use get actor location plus to hit. And we'll multiply this vector by 60 as well. And just like our first arrow, we'll use 5 for the arrow size. For the color, we'll use green. And for the duration, we'll use 5. Okay, so we did a lot here. This is all debug stuff. We're just going to show the value of theta and show these two vectors with debug arrows. All the real work is up here where we're calculating theta. So let's go ahead and compile this and go into the engine, and we can grab a weapon and swing it at the enemy. Let's see what we see. And we see that the angle is 142, which is depicted by those two arrows there. Here we have an angle of 99 degrees. Right here we have a smaller angle, looks like 20. And we can see that with these debug arrows. Right there, 29 degrees. And these arrows do appear to look about correct. Now we do see that the green arrow goes up to the hit location, which is not necessarily parallel with the ground with the forward vector, right? Because we're hitting at basically wherever the sword hits the character. So that's not necessarily going to be a flat vector. Now, if we want a more accurate representation of this angle, we may want that green vector to be parallel with the ground, right? In other words, we want its endpoint's z location to be the same as the endpoint for our red arrow, which is basically the z location of our character itself. And we can do that pretty easily. When we're calculating the to-hit vector, what we're doing is we're getting the vector from the enemy's location to the impact point, but we could instead get the vector from the enemy's location to the impact point lower down to the enemy's elevation, the z value of the enemy's location. So we can make a const f vector called impact lowered and set it to impact point.x for the x, impact point.y for the y, and get actor location.z for the z. So what we're doing here is we can say lower impact point to the enemy's actor location z. And now for to hit, we can use impact lowered instead of impact point. So if we go ahead and save this, we can come back into the editor, do live coding, and then we can grab a weapon, and we should see that that vector is now parallel to the ground, which it is. So it's pointing in the correct direction, but it's flattened out. And that's going to make it a little bit easier for us to determine which direction that hit is coming from. Perfect. So now this makes it a little easier to see that once we get a hit, we can find out whether that green arrow is on the right or the left of the red arrow. So here we see it's to the left and theta is 35. And here we see that it's also to the left, theta is 7 degrees. But if I hit from this side, theta is to the right. So we're getting that arrow in the correct direction. And we're seeing that theta is not ever negative. That's one of the properties of the dot product. It only gives you a positive value. So we need to figure out how we can tell whether it's coming from the right or the left. In other words, whether that angle is positive or negative. And that's going to involve another mathematical concept, which we'll talk about next. Excellent job. I'll see you soon.